Okay, so we're going to move into the second half of this Southwest Marine Ecosystems Cetaceans webinar. I'm going to kick off with a short introduction to cetaceans and the acoustic world that they live in, because that then relates to Joe's talk, who's going to be talking about a cetacean acoustic tracking project that he's overseeing and looking at acoustic detections of cetaceans. How does that pair up with our visual sightings? We'll then be moving into Claire's talk. We'll be talking about cetaceans and offshore wind. There's a bit of an overlap there with noise too. And finally, finishing off with Alessandra, who's giving us an update on the Clean Catch project, which is looking at cetacean bycatch. So again, I'll be sharing my presentation. So that does mean when I do that, I can't see the chat. So again, if other members of the team could monitor the chat for me, that would be great. And shout out if there's any issues during that, so that I know. That'd be good. Right. Okay, so hopefully everyone can see my screen there. So yes, I'm just going to be doing a very brief introduction to cetaceans and the acoustic world that they live in. So just as an outline, I'm going to be talking a little bit about the science of sound and sound in the sea and soundscapes, before moving on to how cetaceans use sound, and then anthropogenic noise or anthropogenic sounds or noise. So the introduction of human-induced sound into the soundscapes and what the impacts on cetaceans from those are. So I really like this graphic from the North. I always get this acronym mixed up, but it's the National Oceanographic and Atmospheric Association from America, but it's basically their big environmental division. So it's quite a nice graphic capture of the soundscape. You can see that the sea is a noisy place. We've got lots of physical noise from things like weather and earthquakes and waves crashing, and then we've got biological noise. As we're looking more and more into the sounds of the sea, we're finding so many animals are producing sounds and using them in different ways, not just cetaceans. We've known cetaceans have done it for quite a while, but we're starting to realize that everything else is using sound as well. And then we've got the anthropogenic sources of noise as well, which I'll talk about. So just a little bit about how we measure sound. Just I'm sure most of you are quite aware of some of these terminology, but just so that you're familiar with this as we're talking through it. Two of the qualities of sound that we most usually reference to are pitch, which is to do with the frequency of the waves of sound. So if you've got short wavelengths, higher frequency sound, that is higher pitched noises. So that's how we detect it or perceive those short wavelengths of sound, whereas deep sounds have longer wavelengths. And we also have a measure of energy, which is how loud that sound is as well. So we perceive quiet or loudness is in terms of the energy within that sound wave. Another thing that you'll find is that low frequency sound, so with a longer wavelength, it takes less energy for it to transfer longer distances in the ocean. And that has repercussions for the way that animals use those sounds, what sounds they make and how and why they're using them. What's also something to bear in mind is that sound is different for not only for different people, but it's obviously very perceptually different for different organisms that are hearing it. So we have a particular range of frequencies that we can hear in, from somewhere in the region of 20 hertz to 20,000 or 20 kilohertz. Whereas you can see that other animals overlap with that and may extend beyond it into ultrasound, so more high pitch sounds, and some go into infrasound. So things like elephants use very low pitch sounds that we can't hear to communicate over vast distances. And it's the same with some of our large whales as well. Whereas things like dolphins and porpoises produce very high frequency sounds, again, that we can't perceive, but they're using those to navigate and communicate. So why does marine life rely so heavily on sound? Um, so sound and vision are two of the main senses we use for being able to perceive our environment beyond just the sort of like the touch of our body, and the immediate sensations around us. And obviously we're very visual creatures generally, so that's for many people is their primary sense. Um, but anybody that's explored the water at all appreciates how limited vision can be. As soon as you put a mask on and go underneath the waves, you start to see it gets darker, it gets bluer, and the best visibility on a dive might be measured in tens of meters. And for anybody going outside, if you walk outside on a normal day and you can only see 10 meters, you'd be terrified. It'd be a really thick fog and you'd be very uncertain about where you were going. And that's because, especially inshore, we've got lots of particles in the water that absorb light. But even in the clearest water, light gets absorbed very quickly. So things rapidly become, distance become undistinguishable. And also, as you go down a few meters under the water, it gets darker. So this photograph is only within sort of 16, one of Matt Slater's great photos, is only within 20 meters of the surface. And you can they're still having to use lights to kind of light up their subject matter to get the colors out of it. Everything would normally be dark and blue to look at down there. Blue is the last wavelength of light that gets absorbed. So for most creatures, they're dealing in conditions that are very dark. They can't rely on sight as their primary sense, and sound travels further and faster underwater, and they're relying on that to give them a lot of the information around about their environment. So how do cetaceans use sound? Well, they use it for all sorts of reasons that I'll just go into a little bit, but they're navigating, to find food, to communicate, cooperate with each other. And some people would suggest they're having conversations too. And I'll just mention some of the research around that as well. I really like this cartoon from Gary Larson. It's a few decades ago. Any of you may remember the Far Side cartoons. I think that kind of summarizes sometimes our attitudes to animals that we're studying in terms of communication. Um, Obviously, these animals use sound similar to we do, so they use it passively by just listening to their environment, and they're getting a great deal of information from that. But they also actively use sound, so they're producing sounds like we do to communicate, but also to help them discover more about their environment as well. So many animals use sound passively, and they can use it for navigation. So there are a lot of auditory cues in the environment. That could be waves crashing on a shore. It could be the sound of, maybe sort of subtler sounds, biogenic noise. As they navigate around, each area is going to sound quite different to them. There's not an awful lot of research on that. It's not something that's really easy to get a handle on, but you can guarantee that they're going to be using that as a cue to navigate. They're also going to be using it as a cue to find food and avoid predators. And this is a little bit of research that was published in 2013 by scientists. They'd used a suction cup to put a hydrophone on killer whales to sort of monitor basically what their auditory environment was. So this one particular sound recording, what the whale was hearing was a seal calling somewhere else, a harbour seal calling, and the male harbour seals will get together and do these acoustic choruses to attract females. And that sound recording got louder and louder and louder of the seal. And then there was a predation sounding noise, and there was no more seal calls. So it just shows that, these animals are listening to sort of hunt out their dinner. So a lot of these animals are also producing sounds, as we know. We've got humpback whales, they're a bit of a favourite of ours at the moment. And so, again, because it's a sort of very limited visual world and it's a very big ocean, and these animals have to find each other over big distances, they use sound to let each other know where they are. And that could be males calling to females. And there's a lot of different species that produce sounds to attract mates. Humpback whales will sing, males will sing in the reproductive season, which has some function in finding females. We're still not fully understanding how that works, but we know it's got something to do with reproduction. And lots of other marine mammals will call as well. So some of our whales, like blue whales and fin whales, produce very low frequency sound that has the possibility to travel over thousands of kilometers. And obviously, like I said, when they're trying to find themselves in find each other in this big global ocean, that's really important. A lot of these animals have social units. So our toothed whales, our porpoises and dolphins, and things like sperm whales, killer whales often live in quite structured family groups, and they'll be calling so that they all know where each other are. So they have this social cohesion. Um, Mothers and calves will often be sharing calls, and I've got this little sound. Oh, I don't know if you'll be able to hear this. I'll try playing it, but this is the sounds that they use, just this whole range of different sounds that they use to just stay in touch, but they're very cryptic and quiet noises because they don't want to alert um, the presence of the killer whales to their presence, basically. That's some fairly recent research looking into the communication there. And we also think that they use these calls to communicate, to cooperate, when they're hunting, trying to sort of like make the group cohesive and work together. With our toothed whales, so again, our porpoises and dolphins and animals like killer whales and sperm whales, these all echolocate, which means they're producing sonar. So they have sound producing organs in their forehead, which produce very, very rapid clicks that they then beam through a fatty structure in their forehead. It's called the melon. It acts as a lens for sound. It means that they send a torch beam of sound out that they use to then any echoes coming back from that, they get a picture, basically an acoustic picture of what's around them, and they can use that for hunting and finding their way about. But as I was saying, our ocean is a very noisy place. It always has been. There's no question of that. It's full of noise, environmental noise, seismic noise from earthquakes, biogenic noise. It's full of high frequency pitch pops and things from invertebrates, grunts and squeals from fish, and everything down to these deep booming calls from whales. But in the last century, it's been also become full of our noise as well. And so some of the sources of this anthropogenic sound, or as we tend to call it, noise, shipping is probably one of the most pervasive and constant background noises now in the marine environment. So NOAA again produced these acoustic maps, and this is a map of the Pacific showing the sound intensity at 50 hertz. And you can see that the entire ocean is full of quite loud noise from that map. We also have construction. So when things like wind farms and things are built, they have to pile drive into the sea floor, into the bedrock to produce firm anchorage. And that is, again, an extremely noisy activity. And then we have things like seismic exploration, where ships are producing sort of air explosions basically behind them, towing them along in what's known as an air gun, produces very loud noises that enable them to map out where oil and gas deposits are under the seabed. We also have sonar from shipping. We have military activities, including really loud sonar in some cases and explosions. And then there are acoustic deterrents which get put on premises where we want to keep animals away from. Things like fish farms can use acoustic deterrent devices. There's a whole source of noise out there. And the impacts of those noise on animals are quite varied. It can be anything from disrupting behaviour, like interrupting sleeping or feeding or mating. It can displace animals from an area if it's loud. It can just move them out. It can also mask their communication calls. So this diagram shows the sort of frequency of sound, the pitch of sound in the middle there on the chart. And you can see you've got seismic, which is like earthquakes and natural noise at the low frequencies, and bubbles and spray at higher frequencies. But you can see here in the middle, we've got shipping traffic. And that sits at the same range of frequencies that baleen whales use. So that can mask out the communication of baleen whales. So I was talking about those long range communications of things like fin whales and blue whales. What we're finding is that, those calls aren't traveling effectively as far because they're drowned out by the shipping traffic noise. It can cause, very loud noises at close proximity can cause hearing damage, which can be temporary or permanent. It can cause animal stress, and there's actually quite a lot of recent research about how this can be damaging for humans as well, that constant background noise. And in the worst case scenarios, it can cause death and strandings. So this is just an example of maybe how animals have adapted to that. Some research that came out in 2007 looked at decades worth of right whale calls in the Pacific. And you can see, so it looked at earlier calls and then compared the frequency to more recent ones. And you can see there's a shift in frequency from sort of deeper sounds in the 1950s, 1970s to higher pitch sounds in the 2000s. And that change was most perceptible in the North Atlantic right, or bigger in the North Atlantic right whales compared to the southern right whales. So there was a bit of an idea here. The southern Pacific is a bit quieter. It's not got so much shipping. So maybe they just, so is it caused by shipping? Is it are they calling higher to make the noise travel better so it's not masked out by that shipping noise? We had a mass stranding in Falmouth in 2008, and we think that was linked to naval activities that was happening offshore. So there was some explosions and sonar, which coincided with common dolphins being inside Falmouth Bay. It drove them, we think, up into the bay, and they panicked. They're in a bit of acoustic panic, and unfortunately 26 did strand. So there's a great effort from British Marine Life Rescued, which saved a lot more dolphins, but unfortunately we did lose quite a few there. And then I did mention that there's more to learn. There's some really interesting little pockets of research out there trying to delve into the communication between some of these toothed whales. They have the ability to send really complex information to each other. And I know one particular research group, which is called Darwin, was using free diving with video and acoustic, hydrophones to look at how sperm whales acted underwater. And they describe it as very much looking like a conversation, because the animal will turn to one animal and click away, and they'll click back and forth between each other using echolocation clicks. And then the first whale would turn and look at another one, and there'd be this exchange. And they said it looks like a conversation. There's the ability there to have really complex information. It's quite tantalizing. Anyway, so we've got a lot to learn yet. If you want to find out more, this is a really great comprehensive web resource called The Discovery of Sound in the Sea, which I love. It's full of resources. It's got lots of webinars but just lots of explanations about how animals use the acoustic world. So do check that out. And that's me on that one. So thank you very much. Right. So I hope that was okay. I shall, without further ado, hand over to Joe, who will be telling you about the acoustic tracking and detections they've been doing on species using FPODs.
Right, lovely. Thank you, Bex. Just sharing the wrong one. Me. Are you seeing that?
Yeah, that looks good.
Great. Okay. Well, as Beck said, we work with acoustics, which is a different way of approaching these trend tracking surveys. What we do that's a bit special is we're listening all the time, every day, every month, winter, summer, day, night, whatever the weather's like. So we see some quite unusual patterns, and this is what I spend a lot of time doing. When we had the pre-meet for this SWME session, I was talking about some data from Wales, and there was quite a bit of interest. So I'm going to go through some of that now. And strictly speaking, it's not Cornwall and Devon, but what's interesting this year is in May, there is a big array of hydrophones going in the Celtic Sea, which will connect us with Wales and lots of other areas, and we'll start seeing these patterns emerge where these animals are coming inshore and offshore and moving between Devon and Cornwall and Wales. So let me move on. I'm looking at four sites here today. So on the left here, you can see there's two inshore sites. This one, the CB4 is Nuki. This one down here, CB5 is Mwent. They're about 20 kilometers apart. Then about 20 kilometers out into the bay at about 44 meters, there's this CB6, Cardigan Bay 6, an offshore site. And then there was some interesting data came in from down here too, in St. Bride's Bay, just off Skoma. And if you look at the chart on this side, you can see that it's gently sloping seabed there. After the 50-meter mark, it does drop off quite quickly to 70 or 80. But for most of this, it's sloping off quite gently. The other interesting thing that I get from Sarah Perry, who monitors this area quite closely, is this inshore area is where the resident bottlenose dolphins in Cardigan Bay spend the vast majority of their time. They are quite close to shore. And out here at 20 kilometers offshore, this is the sort of area where they see far more common dolphins. So the first surprise to me when I looked at the data is looking at these inshore sites, the bottom two, the Mwent and the Nuki, there were far more porpoise detections there than dolphins. This was a bit of a surprise. You'd think the porpoises would avoid the dolphins, but they seem to manage to cohabit in similar areas throughout the year, which was a bit of a surprise. You come up here, the offshore CB6 site, a lot more dolphins than porpoises, and down in Skoma, a lot more dolphins than porpoises. So that was the first surprise. I think the rest of the things we're going to look at are these graphs. Now, the graphs are generated by the FPOD software, and they're averages over an entire deployment. So the top one there, the yellow bars, that's our diel chart. So that's the 0 on the left represents a midnight, 12 in the middle is midday, and the 23 hours there is the following midnight, effectively. So on average, over the whole deployment, these are the number of clicks that appear in each hour. So we can see that there's a nighttime clicking is more popular in most cases. This is the inshore Nuki site, which is likely to be bottlenose dolphins. Mwent here, bottlenose dolphins again, a bit more clicking in the early evening there. And when we get to the offshore site and the Skoma dolphin site, we can see it almost predominantly nighttime clicking. The next one down, the grey, shows the click rates. So starting from 0, it's a logarithmic scale that goes up to around 800 or so. So we've made a sweeping generalization, but we think the lower click rates here are probably echolocation clicks. They're just sort of sweeping a beam around and exploring the world around them. At the higher end here, when they click much faster, given the return time of the sound in water, we think that's the top end of feeding buzzes as they're closing in on the prey and just getting an exact fix on it just before they snatch it out of the water. Their click rates go up well above 800 clicks per second. There are some funny bumps like this, and we have a PhD student at the moment looking at social communication, and that is quite often in these little bumps that appear around these high ends. But these are all dolphin graphs. So you can see in this one, there is really nothing up the top at all. So at Mwent, there didn't seem to be much feeding activity at all, a lot of echolocation. And if there was any social communication there, it was all at quite low click rates there, pretty much below 100 for the vast majority. The click rates in the other two were pretty much as we often see, a lot of echolocation, not much in the middle, and then a lot of top end of feeding buzzes, and much the same at the Skoma. The thing that really leapt out to me when I looked at these, and I haven't seen this really anywhere else on the CAT project, looking at the files from around the UK, it was the bandwidth, the range of frequencies that these animals were using. And as Bex was saying, the dolphins use a very wide range of frequencies. We hear everything in the FPOD from about 17 kilohertz, and we'll go right up to 220. And this is fairly normal for dolphins. They will use a range of frequencies from about 20. We often get a peak around 42, something around 60, something around 120. But that big peak at 22 is really quite unusual. Most animals will normally try and avoid that because that's where all the background noise is, the ambient noise due to sediment transportation, bubble noise. The vast majority of it is down the bottom end there, and particularly in the inshore sites where it is a bit shallower. So that was a surprise to see. Whoops, see that. And at the other inshore side, a bit further down the coast, went much the same thing. In fact, almost totally low frequencies there that they're using, not very little up around 120. So that was a bigger surprise. But this one here, the CB6 offshore dolphins, was the biggest surprise of all. So you can see that this is averaged over 126 days. And in that file, there were 2.5 million clicks that the classifier thought were dolphins. But every single one of those clicks was in this very narrow band of frequencies centered around 42 kilohertz. That was very unusual. I've never seen anything quite like that before. They were clicking all at night time. They were echolocating and they were feeding. I've been right through the file. There is some social communication. There's a whole range of click trains in there, but they were just fixed around that 42 kilohertz. When we go down to SWME, again, a really popular frequency, 43 kilohertz there. There is a little bit at about 120, but really strong peaks down that lower end. Again, these are averages over 155 days, 126 days. So that's really habitual behavior. So we'll move in and look at each of these in a bit more detail. First of all, these are the same pods, the same sites, and these are what the classifier decided were porpoises. This gave me confidence that the pods were all working okay because porpoises are narrowband high-frequency animals. They only click around 120 kilohertz, and that's coming out clearly in all of these detections. So I'm confident that the pods were working properly. And there's something in that environment that it is convincing these dolphins to click at these particular frequencies. So looking at them one at a time, this is the Nuki CB4. This is the inshore site. And there were some other unusual things. That this is 159 days through the winter, and this is 136 days through the summer. So that you can see that this is the bottom one there is the raw data. So this is everything the pod heard. And there are quite similar amounts of background noise. You have 34 million clicks in that 159-day file, and over here there are 25 million clicks in that 136-day file. So a fairly noisy background. The animals right through the seasons, they're just picking this 22 kilohertz as by far their favorite frequency to click at. We can see the summer winter, quite a big difference between the click rates they use. The little peak there for the social communication, the feeding buzzes, that was in the winter. In the summer, there was much less of the high click rate peaks, much more of the lower stuff. And you can see from the diel patterns, there's almost an inverse relationship there, where it's low in the winter, in the middle of the day, it's actually high in the middle of the day in the summer. So these are the sort of anomalies and patterns that we look for in the acoustic data, and this is the benefit of having this constant recording going on for years at a time. We start to see we haven't got quite enough data yet to look for long-term trends. We need several years of data. But what's coming out with the 2 or 3 years we have, we're starting to see these very strong seasonal patterns. So moving slightly down, this is the CB5, this is the other inshore site, and this file on the left, you can see ends at 4th of March. This came in this afternoon. Sarah Perry sent this to me, so I just dropped it in at the last minute. But you can see I circled that there because the difference in the number of clicks here, there were 94 million clicks in the raw data there through the winter, but only 32 million in the summer, so it gets quite noisy in the winter. In the winter, you can see quite different range of frequencies used. There's that 22 kilohertz in the summer that they use extensively. In the winter, a lot more frequencies. Also, we're seeing a lot more of the top end, the feeding and the social communication, whereas in the summer, we are just seeing that low end, the clicking there, maybe echolocation, maybe some social communication. So these patterns start emerging, and they were really strong in Wales, and it would surprise me because 3 of these sites are in a 20-kilometre triangle. They're very close together. So this is the CB6. This is the offshore Cardigan Bay. So this is just 20 kilometers offshore. So, just very close, probably, maybe 20 minutes swimming time for a dolphin to get between these sites. But such dramatically different patterns. Now, there are three on here. Again, there's the winter over here, 126 days from September to February. But this pod rebooted. So it started again on the 13th of February and ran on for another 23 days. So these are effectively the same files. You can see they're very similar there. The frequencies are very similar. But at some point between them changing that on the 7th of March and the 16th of June, you can see there was a dramatic change from the 42 kilohertz that they used right through the winter and right through the spring. When we get to the summer, June to October, they used a whole range of other frequencies, which was a bit of a surprise. I was expecting to see some changes gradually over time, but such a dramatic change so quickly was a big surprise. We can also see from the raw data how noisy this site is in the winter. There's over 200 million clicks in there, and 2.5 million of them were dolphin clicks. So a lot of activity in the winter. And that was over 126 days. If we look at 126 days over the summer, there are only 63 million clicks, so much quieter environment, and only 419,000 of them were dolphins, so less than 500,000 there, more than 2.5 million there over the same 126 days. That, together with the diel pattern there, would suggest that these animals are coming inshore and spending a winter time with lots of nighttime clicking. In the summer, a complete inversion there, completely the opposite pattern on the diel chart. Quite unusual patterns emerging there, but they are quite regular. I'm seeing this in other areas of the southwest too. And down in Skoma, we get a similar thing, slightly different patterns. Again, a strong diel pattern. The click rates are more or less what we would expect. A lot of echolocation, a bit of high-end stuff. But again, the 140 million clicks in that 160-day file, 4.5 million of them were dolphins in the winter. So a lot of dolphin activity in the winter. You compare that with 155 days in the summer, we only get 700,000 dolphin clicks. So a similar favoring of the 43 kilohertz there. But these animals do seem to be coming inshore in the winter and clicking a lot at night. And that becomes obvious when that's the next one. When we start looking at the detection positive minutes of winter versus summer. So the CB6, the blue one is the winter and the yellow one is the summer. So in the offshore site, you see a lot more activity in the winter than the summer. This is the Skoma one, same sort of pattern. That's for dolphins, but the same thing for porpoises too. The offshore Cardigan Bay winter porpoises much bigger than the offshore Cardigan Bay summer porpoises, and the same in Skoma as well. So some really strong patterns there. And Alison Massey, who works on Skoma and gathers this data for me, she does some sightings there, but the sightings are only in the summer. There are some people on the Dale sailing boat cruise who log it as well, and they see quite low numbers here. Some sightings of dolphins, far more porpoises they see than dolphins, which is very different to what we're seeing in the acoustic data. And we think that might be because they're looking here. They're looking in the middle of the day when there's very little activity, and they're looking in the summer when there's significantly less activity. So we think when we take sightings like this, which are done in the summer in the daytime, it is only capturing a small amount of the activity that could be there, and the acoustics is showing all this additional activity through the winter and through the night. So that's something we're seeing throughout the southwest as well. Now, I'll quickly go through these as well because this is a slightly different approach. We have a pod up the Fowl River. I've had it there for about 4 or 5 years now, and you can see it's in there somewhere. This is the pod I put in really, and we use it for testing various equipment that we were using. And I particularly put it there because this biofouling is so bad. That had been in for a few months, absolutely covered in mussels and seaweed. This long trail is all weed just hanging off this pod. So it was a really good site for testing for biofouling. And this goes from March 22 to May 23, and I really wasn't getting any detections along here at all. I wasn't expecting to see any. These are all the boat sonars, boat sonars. And then suddenly, January 2023, I saw this big spike. Suddenly, all these dolphins were coming in and clicking, and that was completely unexpected. We hadn't seen that before in the previous 2 or 3 years. They went again and didn't come back, but the following winter, you can see in November, there was really no detections at all. The orange lines are detections. December, this pod came back and they clicked up the Fowl River there, about 9.5 kilometers up the river, all through December, all through January, through most of February. Then in March, they went out again. These are the again, more graphs. This is when I first saw them. So January 2023, that's when, after not being there for 2 or 3 years, they suddenly came in. And we can see they were coming in about 6 o'clock in the evening, clicking through the night and leaving about 7 or 8 in the morning. And that was confirmed by the people on the pilot boats and the people on the liveaboards. So yeah, we see them coming and going. We can even hear them whistling through the hull of the boat. You can see from the click rates here that there's a lot of echolocation, but there's a lot of high-end stuff here. So quite a bit of feeding activity, quite a bit of social activity. And you can see the raw data here. This is everything the pod heard, and that this is the sort of pattern I would normally expect to see. A lot of low-end noise here. This will be the sediment transportation, the bubble noise. There's a lot in the river there, and we're on an oyster farm, so there may even be some noise coming from the barrels and ropes. But you see the animals. This is the actual clicks of the dolphins. They completely avoid that bit where all the noise is, and they use these other frequencies instead. Now, this was a bit unusual to me. These big peaks around 60, 70, I don't normally see such prominent peaks around there. 120 is a very popular frequency. I see quite a lot of that. But then 11 months later, in the December, when the animals came back, you see the raw data is very similar. The profiles, you've still got all that low end noise, but look at, they were clicking almost identically 11 months later. So I'm almost certain that was the same pod, the same group of animals came in for the same reason and were doing the same thing. You see the dial pattern is very similar and the click rate pattern is very similar too. So I'm fairly certain this was the same group coming in. So that was an 11-month jump. That was December 2023. So then we go into January 2024. And you see it just continues, that these shapes are all very similar. The click patterns are very similar. The dial patterns are very similar. And one of the things that interested me about this pod was the fact that people were telling me that there was a calf there. And I started to think, well, maybe that this 60 kilohertz, maybe this is something that they're doing for the calf. Maybe they bring the calf in and teach it how to fish or how to hunt and how to do various things. So we have another project now where we filter out those frequencies and try and see what's happening in there. And it may be a bit hopeful, but I'm hoping I might be able to see some evidence of sort of young calves learning how to do these things, and maybe the older animals demonstrating, and then the younger animal trying. So it is a little project we've got with some students at the university to look into these slight anomalies and these patterns that are coming out. You see that these are the type of click trains that we were seeing. That's a bit like a feeding buzz. When you get a big upsweep like that, starts fairly low, finishes at about 300 clicks per second. This is in a small river. It really is only about 50 meters wide, and it's only about 12 or 15 meters deep in a deep channel. So there isn't much space there. The pods pick up audio over about 1 kilometer with dolphins. So we are picking them up over a fairly wide range. But we see that feeding activity like this is a continuous file going over a couple of seconds. And then we see long calls like this, which may be social communication. When we see these long wiggly lines and down sweeps, that's less likely to be feeding. And this little yellow bit in here, that could well be another animal sweeping a beam through at the same time. So we look for these patterns and anomalies, but it was the frequencies that interested me. So I started pulling out a lot of other data So I got some offshore data. So from the Channel Islands, from Jersey and Guernsey, I went to the North Coast, Newquay and St Agnes, some open water sites, the Isles of Scilly, Lundy and pt2. And I was finding the dolphins, they click in certain bands. So most of this is the offshore stuff. And they do like these bands between about 20 and 45, a lot of clicks in there. Some of these lines are fairly short, but for instance, the Isles of Scilly one there, that was a 6-month file. So they're just consistently clicking in these rates. The Newquay one here was a whole summer. So they just really moved between 2 frequencies there over the whole summer. These are modal averages. And then the inshore sites, they like the higher frequencies. So between about 105 up to about 121, consistently using those, but really nothing in the middle. They either use the lower ones or the higher ones, except in the Foul River there, where they use all these between about 55 and 70 and up to 90. And that was why those yellow peaks looked unusual to me, because I'm not seeing it in any of these other files, whether they're offshore or inshore. And that's what made me think there may be something a bit special about that. And maybe it had something to do with the fact that there was a calf in that pod. So since then, we've now got a pod about 18 kilometers up the Tamar at Calstock, because I've seen video of porpoises going past the Coat Hill Quay there, 18 kilometres up the river. I'm hoping to get one in the Helford soon. I'm talking to Sue about that. We've got some really nice data from the Isles of Scilly. Briar was mentioned earlier. Briar's actually got a pod out there at the moment, and we're looking for ways of getting that into the sea. But we are seeing a lot of this. I put a pod in the Foy River, and I started detecting a dolphin at the beginning of November last year. And it just seemed like if it was 1 or 2 dolphins, it certainly wasn't a big pod. They were very occasional calls, but they were definite feeding buzzes. They were sort of in the river and moving around. And I got this all the way through November and into December. And then I think later in January, a young male stranded way upstream near Lostwithiel, I think. But it could be that same animal was exploring that river from early November and just went a bit too far and got stranded. But we are seeing this extension of these distributions. These animals do seem to be coming back into the estuaries and rivers. And we're looking for that wherever we can get a pod in the water now. So yeah, thanks to the people in Wales who sent this stuff in, and the SWME Marine Conservation Group who sent me a lot of data to compare it with as well. But there is a website, the catproject.org, where we put a lot of these results and a lot of the data and some of the projects we're looking at. But that's it from me. I know we're running a bit late, so I'll end there and we can move along.
Oh, thanks, Joe. I just find this endlessly fascinating, and it's just so many questions. But I love the idea that a pod of dolphins might have its own little acoustic signature, which makes sense. I think that's really great. I'm sure there's lots of other questions from people, but again, please put them in the chat, and I'm sure Joe will get to them. So we shall. Yes, apologies for running late. Too much enthusiasm from all of us, including me. So I shall now hand over to Claire. Thank you very much.
Thanks, Bax. Hopefully you can all hear me. I'll just share my screen. Can you see that okay?
It's a bit like, oh yeah, that's just come through to full screen. There's a bit of a delay, but it's through fine.
Okay, all good on full screen? Okay. So hi everybody, hope you're all still awake. It's nearly my bedtime, so I'm definitely feeling tired. My name's Claire Owen. I'm a senior specialist in marine mammals at Natural England. In my role at Natural England, I provide advice on the potential impacts of renewable energy projects in English waters. So these are on a strategic level, so looking at impacts from multiple projects in a large area, or on a project level, so looking at the impacts caused by one development. And also we're doing lots of projects to help understand the risk of future marine development and methods to help minimise and mitigate these impacts. So today I'm just going to give a brief overview of offshore wind farms and how they're constructed, discuss the impacts on marine mammals from current offshore wind projects that are constructed or in planning, and focus a little bit on the southwest and discuss how offshore wind in the Celtic Sea could impact marine mammals. So for those of you that don't know much about Natural England, we are the government's advisor for the natural environment, and we help protect and restore the natural world. We were established by an Act of Parliament in 2006, and our purpose is to help conserve, enhance and manage the natural environment for the benefit of present and future generations, thereby contributing to sustainable development. We provide environmental advice to the government in relation to offshore wind policies. This includes advice to the Secretary of State, regulators and developers on potential environmental impacts of offshore wind projects, so that they can avoid, reduce or mitigate any impacts to designated sites and species. We also provide plan level advice to the Crown Estate in relation to leasing of the seabed for each round of offshore wind energy. And we look to identify environmental evidence gaps and help fill those through research. So an offshore wind farm is composed of an array of turbines, all connected with cables. And the cables have been buried in the sea and connected to an offshore substation. And then this has one large cable that connects to an onshore substation and then to the national grid. So all of these elements need to be constructed in an offshore environment. Before this can happen, the area needs to be prepared. For example, removing objects such as unexploded ordnance from the wind farm and cable route areas. During construction of fixed wind turbines, the monopile, which is the cylindrical foundation for the turbine, is piled into the ground using a massive hammer. And then in a separate operation, the turbines are attached. Cable laying vessels will lay the cables and connect them to offshore substations and then to onshore substations. Many offshore wind farms will have 100 or more turbines. So there's a lot of construction in the marine environment. So the UK is now the second largest offshore wind market in the world, generating 24% of the global offshore wind capacity. All on this map here, all of the teal and blue wind farms are operational or in construction, and the construction phase can take years. Green and yellow are in the consent and post-consent stages, where they'll be finalising their design and planning to construct probably within the next 5 years or so. And the red and the grey wind farms are in the early concept and planning stages. So not all of those ones will be constructed, but even just looking at the sort of blue, yellow ones, you can see that our seabeds around the UK are getting very full up with wind farms. So this infographic highlights the environmental impacts of offshore wind, and these ones are known impacts from marine mammals, so pile driving of monopiles and vessel noise, which Bex kind of touched on a little bit earlier. Loud noise is also caused by UXO clearance, so that's when unexploded ordnance, which has been left on the seabed from world wars, needs to be detonated because they are located near the wind farm site or the cable route, and it would be hazardous to construct a wind farm with anything like that around. The noise from those can be incredibly loud and harmful for cetaceans. So these impacts in white, these are possible impacts for marine mammals, but we need a bit more understanding of the extent. So things like electromagnetic fields, changing ecosystem structures from introducing artificial reefs, and changing of the physical processes and fronts. They're all things we need to understand how much that is impacting our marine environment. In addition to this, there was a recent study from the University of Portsmouth that found that the corrosion protection systems, which are on the wind turbine monopiles to stop them from corroding, actually releases large amounts of metals into the marine environment, and the impacts of these on marine mammals need to be explored further as well. You might recognise this image that Bex had in her presentation, and I won't talk too much about underwater sound because Bex gave a really brilliant introduction to that. But marine mammals live underwater, they can't always use sight, and so they rely on sound for communication, foraging, and navigation. Because of this reliance on sound, they have sensitive hearing organs, and therefore they're extremely sensitive to loud noise. Sounds from seismic surveys, underwater explosives, such as the clearance of unexploded ordnance, and pile driving of offshore wind foundations are very, very loud. And this underwater noise can mask communication or foraging sounds, impact socialization, communications between mother and calf pairs, or predator sounds. Noise can also cause behavior disturbance, resulting in animals fleeing from foraging areas, calving areas, or using excess energy to leave an area of high noise. And in extreme circumstances, loud noise can cause temporary or permanent injury and even death. So how do we minimise and mitigate these impacts? So before a project is consented, all potential impacts from the project during construction, operation, and decommissioning are assessed and presented in an environmental statement. For marine mammals, applicants need to conduct a 2-year baseline survey of the project area. This is usually conducted by monthly digital aerial surveys to understand the species that are present at the site and the density of animals. Once they have these densities, the number of animals that could be impacted by the project can be calculated, and the impact significance is predicted. Since the majority of impacts to marine mammals occur during construction, which is the noisy pile driving of monopiles into the seabed, there are guidelines to minimise these impacts, which include having observers on board to ensure that no marine mammals are in the area before piling commences. They use acoustic deterrents to encourage animals to flee the injury areas, and a gradual increase in hammer energy. However, with monopile size increasing, and actually in some of the wind farms in the planning stages, some of them are up to 18 meters in diameter. So they're massive, massive things to hammer into the ground. The impact ranges for marine mammals are increasing as well. So this means that the current mitigation will not reduce the impacts to a negligible level. So consequently, DEFRA have introduced their marine noise package, which was published in January this year. So in this paper, it outlines that the expectation that from January 2025, all wind farm pile driving activity across all English waters will require to demonstrate that they have used best endeavours to deliver noise reductions through the use of primary or secondary noise reduction. So along with this, there were some other papers such as guidance on reducing noise from UXO clearance. So noise abatement systems, which the paper is referring to, any sort of noise reduction technology, is technology that is used to reduce the sound caused by pile driving and to reduce it stop it from entering the marine environment. So examples include bubble curtains, which as this image shows here, you can see there's this monopile that is in the middle that is being hammered into the seabed, and they have this big circle of bubbles all around it, which these bubbles create a barrier limiting the sound which goes into the marine environment. And there are also other technologies which can be used like a soft covering for the hammer to reduce that noise, and there's quite a lot of stuff in development at the moment. So those were the impacts to marine mammals, but you're probably thinking, why are you talking about offshore wind? Because all of that is happening in the North Sea. We're at the Southwest Marine Ecosystems webinar, and how does this relate to the Southwest? Well, if we go back to this map that I showed earlier, and we focus into the Southwest, you can see that there are some early planning potential development zones highlighted here. So the Crown Estate has created 3 areas in the Celtic Sea for offshore wind leasing round 5, which is the next leasing round. And there are already a few demonstration sites in planning. So we have Whitecross with 8 floating turbines off the coast of North Devon, and Twin Hub, which has 2 turbines off of Hale in Cornwall, as well as a couple in Welsh waters. The Celtic Sea is much deeper than the North Sea, which historically has protected it from the offshore wind industry. However, with the invention of floating offshore wind turbines, the Celtic Sea has been identified to have high potential for offshore wind farms. These are the project development sites within Round 5. So at the top of the picture, you've got Wales and North Devon and Lundy Island there. So you can see where these 3 development sites are. So floating offshore wind turbines look similar to fixed turbines above the water, with the tall stem and large turbine blades, but beneath the water, they're very different. There are a few different types, but essentially they float in the water on some sort of platform and are anchored to the seabed. The cables are dynamic within the waterway and will join each platform to a substation or each other and then to a substation. This new floating technology introduces some reduced impacts, but also some potential new impacts. So on a positive, since floating turbines do not have a large monopile to hammer into the ground, but instead are fixed with anchors, if piling does occur, the piles are much smaller and so will likely be much quieter. Since less of the turbine will be in the water, there could be less metals absorbed into the marine environment. However, this new technology does bring some potential new impacts. So the mooring lines and dynamic cables could be an entanglement hazard for cetaceans, particularly large whales. While it's less likely that cetaceans will get entangled in the lines, the biggest impact will be through secondary entanglement in discarded fishing gear or debris, if that's got entangled in the mooring lines or the cables. There's also a potential new impact which has been highlighted by monitoring projects that are looking at existing demonstration flow sites in Scotland. And it appears that some of the configurations of the mooring lines could cause a loud snapping sound during certain sea conditions. And this loud, impulsive sound could potentially be harmful to marine mammals. There's also the potential impact of electromagnetic fields. So an introduction to the dynamic cables that go through the water column to carry the electricity from the turbines to the substation could impact animals which use electromagnetic fields for navigation. Whilst the use of this in marine mammals is really poorly understood, it does need to be considered as a potential impact. And also, floating offshore wind will be in deeper offshore waters and areas that are not already impacted by offshore wind. So introducing structures into this parts of the marine environment could change the ecosystems. Natural England is working with demonstration projects and future Round 5 developers to ensure that these potential impacts are monitored and measured to ensure that we have a thorough understanding of them before full-scale wind farms are constructed. There are also various projects, such as the Celtic Sea Power Subsea Soundscape project, which Joe did touch on a little bit, which is using acoustic arrays to understand the baseline of marine mammals in the Round 5 area. And there's also a project at SAMS in Scotland, which is looking at entanglement of floating offshore wind and marine mammals, and which these will help to fill the evidence gap and inform our understanding of the impacts. So we hope that since we have a better understanding of the impacts of offshore wind farms from the North Sea, and that we can ensure that these impacts are mitigated before construction begins in the Celtic Sea. We also hope to have a thorough understanding of the baseline distribution and abundance of marine mammals before, so we can assess any potential impacts that happen after. So thank you very much for listening, and let me know if we have any questions.
Thank you so much, Claire. Again, really interesting insight. That's really increased my knowledge of floating offshore wind as well. So more to worry about. That's always good. But thank you there. Okay, so again, please, any questions, do drop them into the chat for Claire. I'm sure she'll get to them. So we're going over to our last talk of the evening. Thank you very much for bearing with us. This last one is from Alessandra, who's working for Clean Catch, or CFAS under Clean Catch, but she couldn't be with us live, so she's given me a presentation which is pre-recorded. So bear with me. I'll be presenting it again. If team could monitor in the chat and make sure this is working for me sound-wise, that would be good. But I will share it now. So shout out if it isn't working.
Good evening, everyone, and thanks for inviting me tonight. Unfortunately, I'm not able to join in person, so I'm recording this presentation. If you have any question on this first slide, there's my email, and feel free to send any questions through. I'll be replying as soon as possible. My name is Alessandra Bielli. I'm a fisheries data scientist at CFAS, an executive agency of DEFRA. And today I will talk about the Clean Catch program and particularly the cetacean bycatch mitigation trial. So just for a bit of context, what is Clean Catch? It's a collaborative research program aiming to bring together scientists and fishers with two main goals. One is monitoring, and the other one is help mitigating the accidental capture of wildlife by commercial fishing vessels. It's a program funded by DEFRA, and it's led by a consortium of partners. One of them is CFAS, then we've got Aribada, ZSL, and Mindfully Wired Communications. And we also coordinate activities with the bycatch monitoring program, which has been operational since 1996 and is coordinated by the Sea Mammal Research Unit at the University of St. Andrews. Now, for today I will focus on the mitigation part of Clean Catch. And just again for context, well, there is evidence that there's an overlap of porpoise distribution and static nets efforts in the UK in several areas, and one of those is the southwest of England and Cornwall. So on top of that, around 2017, we've got reports of increasing harbour porpoise bycatch from the fishers from the small-scale net fishery in Cornwall. So they noticed an increase, and they talked to the Cornwall Wildlife Trust, who supported them to initiate this trial. So the cetacean bycatch mitigation trial has two phases. The first one started in 2019 and focused on three different bycatch mitigation technologies. The first two at the top are called pingers, or acoustic deterrent devices. They are basically devices attached to the nets that produce high-pitched sounds that will keep the dolphins away from the nets. And the one at the bottom that was also tested are LEDs, so some green lights that are the same thing but attached to the nets, and through visual cues they aim to reduce bycatch. So the idea was to test these technologies. We asked the fishers to test them for us, so they kept fishing as normal, but they were attaching these devices to their nets, or some of them. We always had a control as well, so nets with no technologies attached, no devices attached. And for the nets that were the experimental ones, so they had different combination of these technologies. Pingers were always 200 meters apart on the net, while the lights needs to be 20 meters apart. So on top of that, the fishers were required to report on any bycatch, but also target catch, and their fishing efforts. So how long were they fishing, how long were their nets, etc. And that was done using a mobile app. And their vessels were also equipped with cameras that were looking at they were filming the fishing activity, the nets, and they were equipped with GPS to track the vessels. And this footage was used as a form of QC for what was reported via the app. So what we had in this experimental, for the experimental design of the first phase was quite complicated. There were different combination of technologies to be applied to the net. Always had to be a control net and an experimental net at the same time in order for us to compare. And then the combination of technologies, of devices was changed, alternated every lunar cycle. We had 3 vessels to start with, but one dropped out quite early in the trial. So in the end, we had 2, and that was between 2019 and 2022. So over 28 months, almost 29 months, we had the 2 vessels that reported over 860 fishing sets, and all bycatch was common dolphins. There was no porpoise, which is interesting because that was the species that seemed to be very high, have high bycatch rates when the trial was initiated. And all common dolphin bycatch was happened in January, February, or December, so in the winter months. The interesting fact is that there was no bycatch ever when LEDs were used. What happened after in 2022 when we started to look at all the information is that we ran a statistical analysis, and this analysis showed that we didn't have enough information to draw statistically valid conclusions about the efficacy of these devices to reduce bycatch. And this analysis also showed that at this rate, we would need another 3 years to have the right amount of information to draw conclusions. So this is mainly due to the fact that bycatch rates were much lower than what we expected during the trial. Obviously, there was a peak towards the beginning when the fishers started to show concerns. But once we started the trial, those bycatch rates dropped. So the lower the bycatch rates, the longer we need to be collecting information in order to compare, if that makes sense. So throughout the trial, we collected feedback from the participants. And interestingly, 2 of the 2 technologies were not fit for purpose, according to the skippers. And one of them was, unfortunately, the lights, which showed a lot of potential because we had no bycatch when lights were used, but because they were not fit for purpose, there was no point. There's no really, they're not useful for the skippers, they're not practical. And the other one was one of the 2 brands of pingers that we tested. Also, and it was breaking a lot. It didn't survive the actual fishing operation, which can be quite harsh. The second comment that was really important is that the experimental design was complex. So it was not practical for the skippers to have to change every lunar cycle the combination of devices placed on their gear. It was really time consuming. And finally, the app was needed to be more flexible and more practical to be used at sea. For example, we had comments about, being on your own on a boat while you're fishing, having gloves on, wet hands, making it really hard to use the app on the spot while they're to report what they're doing. So this was really taking on board to look at phase 2. We, after this analysis and analyzing the comments and the data, we proposed the trial to rethink a little bit and think how to move forward. So the first thing was to decide to test only one pinger type, which was the one that was deemed useful and practical by the fishers. We also decided to increase the number of participants. This is to allow us to basically try to speed up the process, to collect more data in a shorter time, and also hopefully to capture more bycatch events. In fact, by increasing the number of participants, we went from the that little circle in red was the area where the 2 initial skippers were fishing. But in the second phase, the skippers, the fishing area for these skippers is the one in the black polygon there. So much bigger area, and also different types of gears, still nets, but yeah, different gear types, which is interesting to look through as well in terms of what gear is more susceptible of bycatch. So at the moment, we have 9 participating vessels, of which 3 are actively testing the pingers and reporting using the mobile app. We've got other 3 that are on hold. They want to participate, and we're trying to set everything up for them to join. And one of them is actually based in Newquay, so it would add even more an additional area to the fishing extent. We have 2 vessels that since June have been reporting both app and REM data, although there was no bycatch at all, which is very interesting in more than 6 months to have no bycatch. And this is, let's say, not helping to speed up the process in terms of drawing conclusions about the effect of the feasibility and the effects of pingers to reduce bycatch. And then we have 8 vessels that since June have been recording REM data. So they're not reporting pinger information on the pinger experiments through the app yet. They're still getting used to it, but we have a lot of information collected through the footage, so we can also look there at any event of a bycatch event, although this will be looking at all fishing sets, so all type of fishing, even if they're not testing the pingers, will be recording what they're doing. So that's quite useful in terms of having a general idea of what the bycatch rate is as a baseline, even when pingers are not used. Last slide, I think. Yeah, so we've been working a lot in this second phase from the very beginning to trying to communicate as much as possible with the skippers, with the participants, co-designing the experiment from the very beginning to see, to make sure that it's feasible for the participants. Obviously, we've been involving them in all the decision making. You know, they've been discussing a lot with us what's the best for the app as well, for practicality, and then we've been discussing position of cameras on board to capture the best view, and definitely, you know, it's very important to be communicating with them often to clarify the goals, remind them of the goals. Why do you want to be part of that? They all voluntarily start to join the program, but yeah, it's good to keep in touch and, you know, reinforce this kind of team effort and remind of responsibilities and set expectations. It's becoming, the trial is becoming more and more popular in a sense, a lot of people that want to join, and in general, We are just having a lot of positive engagement, and I think this has really been a lot of learning for us as well by working together, and this is just a great example of participatory research, building a team with the skippers, and also building trust between scientists and fishers. And finally, understanding the fishery itself. Yeah, so very, very nice project. This is my last slide. Again, here you should be able to see my email. Please let me know if you have any questions, and thank you very much for listening.
Hopefully you can see the email there. I just it was covered up by my ribbon at the bottom there, I think. I will copy that and put it in the chat to you. Yeah, another really interesting presentation to finish up on. Thank you, those of you bearing with us. It's a long evening of cetaceans. I personally found that really interesting, along a whole suite of different talks. Very great thanks to all our speakers as well for sharing their research and their insights on that. I'm sure you'd all join in and saying thank you. If you do have any questions, hopefully you've managed to pop them into the chat. You're welcome to send me an email to get in touch as well, and I can always pass questions on. But other than that, I think I expect we're all pretty much ready for our beds now.
Thank you, Bex. Well done.
Yeah. Thanks, guys. Apologies for the glitches at the beginning, but thank you for everybody's efforts.
Thanks. Bye-bye.
Bye-bye.
Thanks, Bex.
Thanks. Well done.